Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss EHRENFEST'S theorem and its proof by using HEISENBERG'S equation of motion, or we can say it as equation of motion in quantum mechanics. That's for constant of equation of motion in quantum mechanics. So let's begin. In the previous video lectures, we discussed about EHRENFEST'S theorem and its proof by using the wave function method. But here we have to discuss its proof by using Heisenberg's equation of motion. What is that of EHRENFEST'S theorem? In quantum mechanics, the expectation value of the observables behave in the same way as the observables themselves do in that of classical mechanics. If we consider in one dimensional motion, the equations like m expectation of dx and its differentiation with respect to t, that is m dx, that is the position, it gives rise to momentum. We consider in one dimensional and only in the direction of x axis. Second, d expectation of that of px dt, that is f of x expectation. Let's prove these two equations by using Heisenberg's equation of motion or constant of motion in quantum mechanics. Let's do that proof. We know the rate of change of that observable q, its expectation will be how much? That is minus I by h cross expectation of the commutator of q cap h cap plus the expectation of del q del t. This is the equation that for Heisenberg's equation of motion. Now we have to prove first equation. Therefore we place or we substitute x in place of q. Let us put q is equal to x. We have and look here, since that x does not depend on time explicitly, that means that term will be 0. First we write that will be d by dt expectation of x is equal to minus I by h cross q cap h cap commutator its expectation plus del x by del t expectation. That term will be 0 since x does not depend on time explicitly, or d by dt expectation of x is equal to minus I by h cross, sorry, here we have to put x, that is the x here, as we put q is equal to x, that is x cap h cap commutator and its expectation. That term will be 0. Why that term will be 0? As we write, since x doesn't depend on time explicitly, that's why its differentiation with respect to time will be 0. We have that equation, that equation number 1. Here, where h cap is the Hamiltonian of that of particle, where h cap is the Hamiltonian of the particle of mass m moving in x direction, with linear momentum px, and that Hamiltonian is given as h cap px cap square divided by 2m plus b cap of x, and where b cap x is assumed to be time independent and b cap x is assumed to be time independent. Then we have to evaluate that particular equation by putting the value of h cap here. Therefore, we have to expand the commutator bracket of x cap h cap, that is, when we put the value of h cap here, that will be 1 by 2m commutator of x cap px cap square plus x cap bx x cap vx, the value will be 0 since vx is assumed to be time independent and it is a constant term. The commutation of that commutator bracket of x cap vx will be 0. 1 by 2m, that is x cap, in place of px cap square, that will be px cap and px cap. 1 by 2m x cap px cap a b c, a b commutation of that of c plus c commutation of that of a b, this px cap x cap px cap. Now we know the commutation relation between that of position and momentum will be ih cross when that in the same component x component or y component or z component, that will be ih cross del ij component like this, ij will be 1 here, therefore that value will be 1, that is a Kronecker delta function. That means the commutation relation between that of position and momentum of same component will be IH cross. We have already discussed throughout our videos about the commutation relation of position and momentum, that will be IH cross Px cap plus Px cap, again that value will be IH cross Px cap Px cap IH cross, that means 2 IH cross Px cap 1 by 2m 2 IH cross Px cap 2 cancel out, we only have IH cross divided by m Px cap, that is the value of the commutation of x cap h cap. Now putting this through the equation number 1. Now putting simply mathematical procedure we have to adopt, putting this in equation 1, we get that is d by dt of x expectation, d by dt of expectation of x, that means minus I by h cross expectation of h cap x cap h cap commutation relation, that will be I by h cross by m Px cap expectation, its expectation, that will be minus I by h cross into I by h cross by m expectation of Px cap. I square means minus 1 minus minus plus 1 h cross cancel out, that is Px cap expectation by m, or d by dt of x expectation will be this much. That is the proof of equation number 1. M dx dt Px, that is dx Px, or when m to that side it will be multiplied to that of equation. This is the proof of first equation. Next we have to prove second one. Second one can be proved when we put in place of q as p. That's why that equation changed to a new form and we simplify. Okay, to prove that second one, again let us put q is equal to px. We have q is equal to px in that of Heisenberg's equation of motion or constant of motion in quantum mechanics, that is d by dt of expectation of px is equal to minus I by h cross Px cap h cap x commutator and its expectation plus del Px by del t its expectation. Since Px does not have explicitly time dependence, that's why that term will be 0, since Px doesn't have explicitly time dependence. Let us that equation will be changed to Px expectation minus I by h cross Px cap h cap x commutation and its expectation. Let us, our task is to evaluate that particular expectation value. Let us evaluate. Therefore, just prefer it as a equation number 2. Therefore, Px cap h cap of x its commutation. Just put the Hamiltonian value here. We have 1 by 2m Px cap Px square plus Px cap Bx. Its value will be 0. Only sorry that value not 0, that value will be 0 when it will be the same term, that value will be exist. That means we have Px cap B cap of x. Okay, that value is exist. Again we have to evaluate that one. Again let we choose an arbitrary wave function psi Px cap B cap x acted upon that wave function psi. We have Px cap B cap x psi minus B cap x Px cap psi. Px cap that is V psi minus V Px cap value h cross by I del psi by del x. Here the value of Px cap that is also h cross by I del by del x, when del by del x of a V psi, two terms are multiplied and its differentiation means the derivative of first term, second term treated as constant, and derivative of second term, first term treated as constant. H cross by I del V by del x of psi plus H cross by I del psi by del x V minus V H cross by I del psi by del x. Look here, these two terms are cancelled with each other. Only that term exists, that is H cross by I del V by del x act over psi. Since psi is arbitrary constant, arbitrary chosen, then Px cap Bx cap is equal to H cross by I del V by del x. Now put the value of Px cap H cap x commutator bracket in that of equation number 2. What we have? Putting this in equation number 2, we get d by dt of px cap expectation minus I by h cross into h cross by I. Its expectation means h cross by I del v by del x expectation minus I by h cross by I del v by del x expectation. H cancel out, I cancel out, that is the negative of potential gradient. That entire term will be the expectation of f of x d by dt of px cap expectation, where f of x, that is the negative of potential gradient del v by del x in that of conservative force. The force is conservative force. This is the proof of EHRENFEST'S theorem. Now, combiningly these two, we say the EHRENFEST'S theorem and its proof by using HEISENBERG'S equation of motion. First equation is proved. Next equation will be proved by putting q is equal to px, and similar manner we proceed. And finally, proof that equation number 2. So, with this useful and informative notes, let me wind up this session. Thank you.